In the summer of 1997, deep beneath the surface of the southern Pacific Ocean, a sound traveled. It moved not through air, not through rock, but through a thin, invisible corridor of cold water where pressure and temperature conspire to trap acoustic energy and carry it across impossible distances. The sound rose in frequency, slowly, over roughly 1 minute. It was broadband. It was powerful. And when it finally reached the hydrophones of NOAA's autonomous underwater listening network, it did so on instruments separated by more than 3,200 kilometers. The same sound, arriving at multiple stations from somewhere in the deep south. Scientists gave it a name that captured the texture of the recording rather than its origin. They called it the bloop. To understand what was heard, you have to understand where it was heard. NOAA was operating its hydrophone arrays at the time to monitor underwater volcanic activity in the southern Pacific. These instruments sit anchored in the deep ocean, listening continuously, recording everything the water carries to them. The network was not designed to solve mysteries. It was designed to watch the seafloor breathe. But in 1997, it caught something that did not fit the usual catalog of submarine volcanoes, distant earthquakes, or passing ships. The signal's arrival direction, the azimuth established from the way it reached different hydrophones at slightly different times, pointed broadly toward the Antarctic, toward a region spanning roughly from the Bransfield Straits to the Ross Sea, or near Cape Adare. That is a vast arc of ocean and ice at the bottom of the world. It told scientists where to look. It did not tell them exactly what they were looking for. The ocean environment that produced this sound is one of the most extreme and least visited on Earth. Antarctic waters host enormous drifting icebergs. They calve from ice shelves, run aground, fracture, grind, and disintegrate. Throughout that process, they are mechanically active. They flex, they crack, they grind, and when ice of that mass fractures suddenly, it releases energy. The ocean is not silent around Antarctica. It is filled with acoustic noise from ice, from marine life, from distant ship traffic, from the seismic tremor of the planet itself. Parsing that noise, identifying individual sources within it, requires both sensitive instruments and careful analysis. The question scientists faced after 1997 was whether the bloop's specific acoustic signature could be matched to any known source category. Initially, it could not be cleanly matched. The bloop's spectral shape, the way its energy was distributed across frequencies, and the way that frequency profile rose over time was unusual enough that classification was not immediate. This is where the internet found its foothold. The recordings circulated. People listened. Because NOAA's posted audio sample plays the signal at 16 times its actual speed, what listeners heard was a strange, almost biological-sounding noise compressed into a few audible seconds. At natural speed, the sound unfolds far more slowly, over roughly 1 minute. But the sped-up version invited speculation. Could something alive have made this? Something very large? The official NOAA evidence did not support that interpretation, and later acoustic comparisons argued against it. The investigation that resolved the question was not a single expedition. It was an accumulation of observations made across the years following 1997. NOAA's Pacific Marine Environmental Laboratory acoustics program continued monitoring the Southern Ocean. Hydrophones deployed nearer to Antarctica began building a richer catalog of the sounds produced by ice. Icequakes generated when large icebergs fracture, grind against the seafloor, or disintegrate under internal stress. Researchers, including teams from NOAA and Oregon State University, analyzed these signals in detail, comparing their spectrograms to the library of known underwater sound sources. The comparison set included whale vocalizations, earthquake signals, ship noise, and iceberg-generated sounds. The methodology was systematic. The goal was classification, not confirmation of any preferred answer. What emerged from that work was a consistent pattern. Icequakes, the acoustic events produced by large iceberg fracture, generate broadband, short-duration signals. Their spectrograms show characteristic shapes. And critically, later icequake signals recorded from Antarctic icebergs matched the bloop spectrogram with notable similarity. By 2005, NOAA had identified the source class as an icequake, the cracking or fracture of a large iceberg. In 2008, a tracked iceberg, A53a, produced comparable sounds, providing later corroboration of the mechanism rather than a retroactive identification of the 1997 source. A53a did not cause the bloop. It showed that icebergs can and do produce sounds that look like the bloop. The physical pathway that carried the signal to those distant hydrophones is itself a remarkable feature of ocean physics. The ocean contains a natural sound channel, a layer where the speed of sound reaches a minimum, trapped between colder water above and higher pressure water below. Low-frequency acoustic energy generated within this channel can propagate for hundreds or even thousands of kilometers with relatively little loss. NOAA's hydrophone network is positioned to exploit this channel. It is why a single event near Antarctica could be detected on instruments more than 5,000 kilometers away. Distance alone was never evidence of an extraordinary source. It was evidence of an ordinary physical channel doing exactly what physics predicts. The identification rested on 3 lines of evidence. The signal's acoustic and spectral character matched what Antarctic icequakes produce. The propagation physics of the ocean sound channel explained how such a signal could reach distant hydrophones, and the arrival direction pointed toward a known region of Antarctic ice activity. The mystery had persisted for years, not decades. The resolution was not dramatic, it was methodical. What remains unresolved is narrower than it might sound. Scientists cannot identify with certainty which specific iceberg fractured, at which exact coordinates, at which precise moment in 1997. No simultaneous visual observation documented the event. The individual geometry of the source remains unconfirmed. That narrower uncertainty does not reopen the biological speculation. But the source class, what kind of process produced the sound, is not scientifically open. It is ice. The bloop became famous partly because the ocean still earns that fame. These are environments that resist direct observation. Sending instruments to the deep southern ocean is expensive, logistically demanding, and often limited by weather and sea state. A sound detected in 1997 could not immediately be traced to a specific event because no network was watching the specific place at the specific moment. That gap between detection and direct observation is real. It is not a gap filled by invoking unknown creatures. It is filled incrementally by more instruments, more data, and more careful analysis. That is what happened here. The ocean transmits information across thousands of kilometers through physics we understand. It hides the precise details of individual events behind distance and the absence of eyes in the right place at the right time. What recorded the bloop was a network built to listen. What explained it was ice, vast, ancient, mechanically stressed ice, fracturing in the cold at the bottom of the world, releasing a sound that traveled farther than most things travel, and arriving finally at instruments that knew how to receive it, but needed years to fully understand what they had been told.